the things I need to emphasize, because I don't want to get lost in certain details by ignoring some of the big parts of this. So I want to do 2 examples today, and if there's time, we'll do a third, but I doubt it. So I want to do the infinite line and the infinite sheet of charge. And I want to do these 2 particular examples. And I want to, start with the infinite line of charge, and we'll talk about the types of things we need to do to do this problem, but we're also going to talk about some assumptions we're making so that we understand the limits of what we're actually doing. So let's start with that. Let's start with a finite line of charge. I want you to imagine if I have a finite line of charge, again, whose charge is Q and length is L. It has an electric field that has certain properties that you would probably expect. And what I mean by that is just consider a point charge placed here compared to a point charge placed here. These are things we were talking about yesterday. But then a point charge placed here or a point charge placed here. Can you imagine that probably towards the center of the bar, the electric field is probably pretty uniform, extending away from the bar in all directions. I can only draw this 2-dimensionally, but we understand that there's probably some circular symmetry. We described that yesterday. So if I was looking down the length of the bar, then we probably have an electric field that looks something like this. Right? Talked about this yesterday. All good so far? Now, I know that as I get closer to the sides here, it's probably not going to be pointing strictly away from the bar. Because as I get close to the sides, I'm going to have more bar on one side than the other. So I think as I start getting away from the center, I bet the electric field starts to push away. And that probably happens all around the bar because I have more bar on one side than the other. But as I get closer to the center, it probably gets more collimated. Does that make sense? Now, that's one of the things about, go ahead.
What do you mean by more bar on one side?
If I'm here, there's more bar here than there is here. That's all I mean. Do you understand how that would push the electric field more at an angle?
Yes.
Okay. So when I'm closer to the center of the bar, I expect the electric field to be more uniformly parallel than when I'm at the edges. In fact, you will hear me say the words edge effects quite frequently in here. Because as long as I'm near the center of the bar, I probably have more uniformity of electric field than when I'm near the edge. So the effect the edges have on my problem can be minimized if I stay closer to the center of the bar. Is that phrase okay with all of you? I'm speaking slow and diplomatic. Meaning, I think those edge effects mean less if I'm here than if I'm here. Right? Closer to the center of the bar. Because when I'm closer to the center, I have a lot of bar on both sides of me, and I'm very close to it. But if I get further away, the bar is appearing to get smaller with respect to where I am. Its ends coming more into focus. In fact, the further away I get, the more the bar becomes a point mass or a point charge. So when I'm close to the bar, it's expansive with lots of bar on either side. And so when I talk about the infinite bar or the infinite line of charge, what we're really instantiating is the idea that I'm talking about a situation in which I'm close enough to the bar for the field lines to be pretty collimated and parallel. That's what I'm saying. It's not a trick. I'm not hand waving. The reality is what I'm about to solve only really means that I'm finding an electric field near the center of a long bar compared to how far away I am from the bar. That if I get towards the edge of this bar, I will have edge effects that will distort the field, and it won't be exactly what I'm solving for here. Does that make what I'm solving for less useful? In some cases, yes. It means if I build something where the charge of a line or a charge of a bar matters, and I base it on the electric field I'm about to use, then I'm probably not going to be within the same tolerance of a measured value if I actually build it as to what I predict it will do. This is why everything we build has tolerances, because we built it usually based on theoretical specs. But those theoretical specs are in themselves based on some assumptions that you've made. So if you don't want to make these assumptions, you may have to change how you figure out the electric field. So perhaps you're not going to be up close to the bar. Perhaps you're going to be far enough away where the bar's length is going to matter. Well, then this probably won't be the way you should solve for the electric field. Here's what we're going to do. We're going to make some assumptions here. And again, like I said, these assumptions they're not necessarily unrealistic, but you have to understand the limits of your assumption. So one of the limits of our assumption is that if your bar isn't going to be very big compared to how far away you are, don't use this method. But if you can get close enough to the bar where the bar is very big, you should be able to use this idea. So we're gonna get really close to that's the opposite. We're gonna get very close to the bar. Okay, so that we are very close to our charge bar. But our charge bar still has charge Q, and we're gonna say it has length L, or we're gonna say that it has a charge density of Q over L. Doesn't matter which one of these we choose to use. I think at the end of the day, we'll probably leave it in terms of lambda. I think you'll be happier about that. But remember what lambda is, just Q over L. I've gotten myself in trouble with my other students in past years by not emphasizing that lambda is just coulombs per meter, charge per unit length. So don't get confused, but also yet it's one more in a long line of symbols, because lambda could be something like A times X, where the charge density gets bigger as I go in the positive X direction. Right? Now that would be a non-uniform charge density. So don't worry too much, except if you can do something with a uniform charge density, you might be asked to do something with a non-uniform charge density. So we need to be careful, understand what the terminology is going to be, but don't be scared away by symbols. Just know what they represent. Lambda is always going to be used for linear charge density, always in this class. It's always going to be the charge per unit length. So in your head, it's just Q over L. All right. Like I said, I want to use Gauss's law. Gauss's law has two parts, the enclosed charge and the flux. And to try and not confuse you as much as I probably already have, I'm going to be very careful about writing my symbology as formally as I can. Now, I want to talk about calculating the flux first, because we really haven't done that in a very sophisticated manner. So I want to do that here. And I'll remind you that flux is trying to calculate the sum of the electric field as it passes through a closed and bounded area. So to do so, I will need to have a mental image of what I think that electric field is before I even start. And I do. I believe my electric field has a look to it like this. Nice, uniform, collimated field lines spreading away from the bar in a 360-degree pattern. So there's this, which is just us looking at the bar, but I'll remind you, there's this looking down the bar. Okay with these two pictures? Now, if you're a person who likes to have steps, once you have a mental image of what your electric field is, step one, you need to create a Gaussian surface. That term will be on your test. Gaussian surface. Remember, Gauss's law is about an electric field that passes through a surface. It's not really about a real surface. It's about a mental exercise about a surface you create in use of Gauss's law. So we are creating the Gaussian surface we will use. And we want to choose a surface that exploits the symmetry of the problem. We're looking for two things here. We're looking for a surface that will have parts where the electric field is a constant on the surface, or parts where the electric flux is zero. That's what we're trying to find whenever we do this. So I'll say it again. We're trying to find a surface where the electric field is a constant everywhere on the surface. It doesn't have to be aligned with the surface. That would be nice. But at least a constant everywhere on the surface. That's our first goal, to find surfaces that either have a constant electric field on the surface or have no electric flux. That's what we want to create, that kind of surface. So yesterday we talked about the surface we would use here, and it was a cylinder. So a cylinder. This is my Gaussian surface that I'm going to use. Now, I want to use both pictures, so I'm going to draw my cylinder here too. But remember here, looking down the wire, my cylinder is going to look like this, right? It's going to be just the outer edges of it. The top and bottom are hard to picture here, but I point out that if we do this right, we want to make it concentric so that this distance, which yesterday I used z because we were a distance z away, or the idea is that this surface is at the point z that we marked yesterday. So I forgot to write that in from yesterday, but point z was like right here. We want to find the electric field here. Point z away. But this distance serves as our radius for our cylinder. Did I use a capital R or I just use Z, but it serves as the radius of our cylinder. Now, I chose this particular surface because of a couple of things. First, I don't really know what the electric field is, but I think the electric field will be the same size as long as I am the same distance away from the wire. Doesn't that make reasonable sense? And I think there's a lot of reasons to believe that would be true. Also, the electric field is radial. This hits at the next thing we're trying to do. Pay attention to the flux. I think this electric field is aligned with the area in the same way that it was aligned with the area for the point charge. I think the area along the outside of the can, or outside of my cylinder, will always be in the same direction as the electric field. Right? Just like this picture I drew. Because the electric field is going to be going through the outsides of the can, and my area is always pointing away from the outsides of the can. So I think we can deal with the outside portion of the can pretty easily. Still all good so far? So I'm trying to address the total flux. The problem is that my surface actually has 3 surface areas. There's the top of the can, there's the bottom of the can, and then there's the sides of the can. Do you guys see that? Well, the top of the can has an area that's this way. That would be the direction of the area of the top of the can. And the bottom of the can would have an area that's this way. That'll be the direction of the bottom of the can's area. But the sides of the can, of course, have a direction this way, as we just explained a minute ago. But I did this purposefully because I tried to set up my can, set up my cylinder, so that there was no flux through the top and the bottom of the can. No field lines that pass through the top and the bottom of the can. Do you guys see why that must be true? Yeah. I made the area perpendicular to the electric field. Let's focus on the math for just a minute, because that's what we're here for, right? Let's take that expression that says I have to add up the electric field for the entire area, and realize as long as I add up the electric field for the entire area, I have served this purpose. So I'm going to have the electric field over the entire area for the top of the can plus the electric field times the direction of the area for the sides of the can plus the electric field times the area for the bottom of the can. Notice I've taken a little circle off the integral. That's on purpose because I've broken it up into 3 partial areas. So separately, each piece isn't the whole area, it's just a partial area, but it's a sum, so if I add them all together, I get the total area. All good so far? Okay, go ahead.
Is it possible that we can do like 2 times the top? I know that,
It's possible, but it's not going to matter.
okay.
So just let me get to another part here, please. I want to finish before the bell rings. I don't even think I'm going to. The top's going to be 0, right? Because the cosine there is going to be 90 degrees. Bottom's going to be 0 because the cosine there, 90 degrees. Thus, I don't need to double it. They're both 0. On the other hand, the cosine here is going to be 0 degrees. But the electric field will be a constant everywhere. So, technically, that's what I'm going to have to do for my flux. The thing is, this is the area of the outside of a can, just the sides, which I'm sure you did what I suggested, which was go home and look it up, which is 2 pi r times the height of the can, right? So apparently it does matter how tall my can is. Height will be this measurement. So for us, our flux becomes epsilon naught E times 2 pi Z times the height of our can. How much charge is enclosed? Well, charge is enclosed from here to here. Isn't this length? Isn't this length just h, the height of the can? That means our charge enclosed is lambda times h, right? Charge per unit length times the amount of charge inside the can. Well, everything there's a constant except for E, Right? We can just solve this for E and have the electric field near the outside of our Gaussian surface. So I cancel out the H's, and I'll get lambda over 2 pi epsilon naught times Z. There's some ramifications for this for tomorrow. We will review what we did here before we get started too much tomorrow. But there it is. That's why I wanted to get back to this. We were rushing towards the end. And I don't want to be rushing. I am trying to be very slow and diplomatic with this. And that's purposeful because you rush the end, you miss the parts. And you don't get a chance to get your notes down. So I do want to go back a little bit because we were moving really fast here. So let's switch back to where we were right here. Is that okay? And kind of come back at this. So if you'll recall, we took and broke this up into 3 separate integrals because we have a surface that has a top, a bottom, and a side. And then we used mostly the dot product to eliminate 2 of them. And we did that because the dot product in this circumstance helps us realize that if we look at the top and bottom, the direction of the electric field is perpendicular to the direction of the area, right? So we did that on purpose, right? We designed our Gaussian surface so that we could say that. Does that make sense? Now, that meant that only this portion is the part that contributes to any meaningful flux from the long straight wire, correct? So with that in mind, that led to us looking at the flux from just that portion. I pulled the electric field out because it's a constant everywhere on the outside of that surface, and all I have to do is sum up the entire area of the outside of the can. But I know there's some people who don't know where this came from for the area of the outside of the can. So let me just tell you, if you cut a can, it will be a rectangle, right? And because we are dealing with a can, our entire flux would look like this. Except I'm going to replace R with Z because the variable that we are using to represent the radius was Z. Because our original problem was about finding the electric field a distance Z away from our long charged wire. They're all better. So this is the total flux, a distance Z away. We've evaluated the top, bottom, and sides of our cylinder. Now, our next step is to drop this into Gauss's law, which is to go ahead and include what Matthias just brought up, that if this is our total flux, Q enclosed has to equal epsilon naught times the total electric flux, which for us will be E 2 pi times Z times H. But that brings us to Q enclosed. And this is where we had to start rushing, but look at the picture again. Q enclosed is how much of our charged wire is trapped inside the can. Well, that's going to be cut off from one side of the can to the other side of the can. So I have trapped a wire that is H long inside the can. Everybody got that part too? Because that's important here. Since I've trapped that much of the wire inside the can, that's going to determine how much charge there is. Now, we said that the entire wire has a linear charge density of lambda, which is the charge per unit length. So if I want to know how much charge is enclosed, I just have to multiply H times lambda. So this has to equal H times lambda. if you want it, if you were given different stuff, this could have been H times Q over L. Right? Those would mean the same thing. So if we had a bar of charge of charge Q length L, and we were very close to it at the center, right? We would need to say all those things to be able to use Q over L, but we could have Q over L there too. It's traditional for this solution to be in terms of lambda, so I'm going to have our traditional solution in terms of lambda. So I'll solve for the electric field here, and the electric field is going to be lambda over 2 pi epsilon naught times z. Now this is what we had yesterday, but we were going fast. I want to put this in a little bit of perspective. The electric field decays, right? Further away I get from the long charged wire, the smaller the electric field gets. Does that make sense to you, that it would get weaker as you got further away? Does it attenuate as much as a point charge attenuates? No. If we look at a point charge is Q over 4 pi epsilon naught times r squared, where r squared is how far away from the point charge we are. So clearly, the point charge attenuates faster than a line of charge. You guys see that? That's because it's spread out. And because of that, it attenuates less. Go ahead.
So why does the charge get close?
So this gives us kind of a picture of two of our major structures, a point charge's electric field and our long line of charges electric field. Now again, in the reality here, it's not an infinite line. It's the electric field near a charged bar or a charged line when we're close to it. Remember that I have to keep emphasizing that if it's an actual bar, as long as we're really close compared to its length, we get this structure for the electric field. As soon as that's not true, this isn't true any longer either. We would have a more complicated expression for the electric field, but we wouldn't be able to use Gauss's law for that. Gauss's law is kind of designed for these kinds of situations. Yes, Sahana?
So it doesn't matter.
We're saying that H cancels out, and we're saying it doesn't matter, but it's not that it doesn't matter. Explain this, or at least try and answer your question as to what do I mean by charge enclosed. Here's our can, and here's our bar, right? And our can is H tall, right? Now, if I actually have a can, and I hold it up to you just right, from your perspective, this probably looks like a rectangle to you, doesn't it? Is that okay? With this being H. So if I take this and say that I'm putting it there, how much of my wire is inside the box? A length of H, right? The only part of the wire that's inside the box is the part from here to here. Is this inside the box? And is this inside the box? No. Gauss's law only speaks to the charge that's enclosed in your bound surface. So this is the only part of the wire from here to here that's inside the box. So it's the only part of the charge that is contributing to the electric flux, right? But I have to know how much charge there is. Right now I know the length of the amount, but I need to convert that to charge. Well, lambda is charge per unit length. It is the charge density. It's how much charge I have per length. And H is a length. So if I take lambda and multiply by H, I get how much charge there was. Okay. We're sure? Because I'm going to go one step further, because I don't want this question later. Lambda could also have been written as Q over L. The total charge of the bar divided by the total bar's length. Well, the charge enclosed would be proportional in this fraction, right? Same thing. So I would just multiply both sides by h, and that would give me my charge enclosed, correct? All good? Excellent. Let me go back to this picture and see if I can do something here. If I were to make the can bigger, I am increasing the total flux now, right? But I'm also increasing the total amount of charge enclosed. So under that circumstance, the flux changed because I enclosed more charge. So that's why it canceled out. I don't want to say it doesn't matter. That's why it canceled out. That's different than the same argument here. I really wouldn't want to use, say, I don't know. Oh, that doesn't look right. A surface like this, right? That would be a bad choice for my Gaussian surface because I don't get the exploitable symmetry here. Right? And I think that if I'm closer to the line, I'm probably going to have a stronger electric field, and every single point on this surface is at a different angle relative to the electric field. This is a poor choice. All good? Following along okay so far? Because at this point, we still have one more to go. Probably one of the harder ones for us to discuss, and that's going to be an infinite sheet of charge. Please, for my own sanity, tell me that I don't have to describe infinity anymore. So I'm going to draw this a couple different ways in the beginning to kind of get us launched into this problem. But there are some things here about a sheet of charge that we will have to define. The first one is the charge sheet, if we're saying it's infinitely big. There's a lot of different infinitely big charge sheets that actually have shapes. So if I have a disk of charge, but I'm very close to its center, that's still going to be treated as an infinite sheet. If I have a square or rectangle of charge, but I'm very close to its center, I'm still going to treat it as an infinite sheet. It still comes back down to the idea that if I turn either of these on their side, they look basically like a line of charge. And if I am close to the center of them, so I'm very close to their center relative to their size, I can treat them as an infinite sheet. Is that all okay? Now, again, edge effects. That works great until they're no longer really infinite. So that means if I'm over here near the edge, I can't really treat it like an infinite sheet anymore. And if I'm dealing with the fact that maybe I'm very far away, I can't really treat it as an infinite sheet anymore. Right? When we say infinite sheet, what we really mean is that we're very close compared to its dimensions. But with the infinite line, I could just say that L was much greater than Z, right? Where Z was my distance away from the line. I don't have an easy dimension to put here. If it's a square, I guess Z is very small compared to the side length of the square. Or if it's a circle, Z is very small compared to the radius of the circle. But there's just too many different shapes, octagons, pentagons, I don't know. So let me just say that as long as you're near the center and you're close to the surface, we can treat that object as if it's a infinitely large sheet, okay? There's going to be other geometries that are also going to have to allow us a certain amount of flexibility in their shape, and we'll get to them later, but I want to start with that. And on that topic, I'm just going to say that it has area A. I'm not going to define it outside of that. It could have area pi r squared. It could have area side times side. I don't care. But we're just going to say the area is A, and it has total charge Q. And this is a surface charge density. That's the phrasing that we will use, surface charge density. I'll often just shorten that to to charge density, but it's a surface charge density, and that would be charge per unit area. Right, something like coulombs per meter squared. The symbol used for this is lowercase sigma. That's the traditional symbol given to charge density. We're going to use lowercase sigma for this. Now, it's hard for me to describe the surface we're going to use here. I like to use a cylinder, but we could use any number of surfaces. So I'm going to draw it this way, and it's not meant to be confusing, but you'll probably find it to be confusing, so I don't really care. But you know, what can I do? You know, this doesn't look like I want it to look, so by the time I get it drawn, the bell will ring. So I'm going to take the sheet, turn it on its side, and the kind of surface I want to use is kind of a can again that is both above and below the surface of the sheet. You follow what I'm trying to do? I don't have a good way to draw this, so I'm going to do my best. So in this drawing, I'm going to say that this is H above and H below. I'm going to try and put it so that it's perpendicular through the surface, and the top has radius capital R. That all okay? Now, can we also agree that probably the electric field coming off of this is going to be in parallel kind of electric field lines everywhere away from the sheet? Does that make reasonable sense? So with that being said, is it not too crazy to realize that I'm probably going to do something very similar when it comes to dealing with the flux? That although this is our technical definition, that I'll probably break this up into top, bottoms, and sides? Do we all see that? But do we also see that probably no flux through the sides this time and only flux through the top and bottom? If I line it up just right, would you agree? And can we also agree that if I make sure H is the same on both, that the electric field at the point where it reaches the top would be the same as the electric field at the point where it reaches the bottom? Is it also true that the electric field that's going through the bottom pierces that surface in the direction of the area, because the area at the bottom would be this way? Is that true? Electric field's going to be going down underneath the sheet, and the area of the top will be downwards underneath the sheet. And at the top, the area is going up, and the electric field would be going through that top in the direction of up too. Does all that make sense? Yes. Trying to build the idea that I'm going to have the sum of the electric field for the top plus the sum for the electric field for the bottom, but the sum of the electric field for the sides is going to be 0. That all okay? Does that make sense? All right. With that, I think I'm going to have E times pi r squared for the top. plus E times pi r squared for the bottom. Does that make sense? So my total flux looks to be two E pi r squared. Does that make sense? Now, how much charge is enclosed? Do you notice I'm enclosing a disk worth of the sheet? That this is how much charge is enclosed. A disk worth of the sheet. And that area of that disk would be, Q enclosed, is going to be sigma times pi r squared. Charge per unit area times the area of the disk. Now, I hate to do this, but I can't not finish. Because you need to see this. I just put the two things together, right? Do you see pi r squared and pi r squared goes away? That means our electric field is a constant near an infinite sheet. It doesn't degrade, it doesn't decay. It's constant, uniform electric field near a sheet of charge. That's an incredibly important observation. And it doesn't matter. And I don't know why I'm spending so much time on this, but there's something in the back of my mind that says, if I do this, I will help you in the future. If it was the point charge, and we decided to say something similar, like, what if I made this bigger? Does it matter? Well, this time it matters. Because under this circumstance, by expanding the size of my area, I am not enclosing any more charge. And I'm actually not changing the flux either. But I'm further away. So the size of the electric field at this point has changed. But I also have a larger area. So that's why in this case, if I change this geometry, making the surface bigger, I do change the electric field that I find, because now R is further away, but I never change the flux, right? So when we talk about changing the geometry, sometimes changing the geometry will give you a different answer. I will point out two things that are important here, and I'm doing this just to try and screw with you a little bit, so keep that in mind. If I had instead put a box around my point charge and put it at the center of the box, am I now enclosing more flux? No, right? Because I have the same charge enclosed, so I would still have the same flux. But would this be an appropriate Gaussian surface if I was trying to find the electric field? No, I lose the symmetry that would have made this useful. So, and I think we all know that the electric field here is going to be different than the electric field here because one of them is further away than the other. So there are some surfaces that are better to use. I could make